Okay, we want to welcome you to 13 Nights of Halloween. This is night, I think 9. Yes, tonight is night 9. This is the Willamette University Chemistry Club. Can you guys give them a big round of applause, please? Okay, half of you are still in story time mode. Can we do like a rock and roll clap for them, please? That's more like it.
My name is Emily, and I am one of the presidents of Chemistry Club, and these are the rest of our members. So we are, and they all say hi, they're all awesome. So to start things off, I'm going to pass the mic to one of our members who's going to talk to you a little bit about chemistry.
Okay, so can anyone tell me, can anyone hear me? Everyone can hear me? Okay, can anyone tell me what chemistry is? No?
It's when you have a really good connection with another person.
That's a different type. Yes. Science, yes. How about you?
Chemical reaction and change. And let's see. I'm not really sure.
Yes. Yes, it is. It is a chemical change. What sorts of change do we see every day? Can anyone tell me? Does anyone know?
Physical and chemical change?
Like an example, you know? Yes.
Condensation and evaporation. Every day we see dew fall on the ground, and by mid-morning it's gone back into the air.
Yes. Other things that we see are ice melting, fireworks exploding, and the digestive and metabolizing of food. These examples are chemical reactions that involve change in matter and the material that make up everything in the universe.
So chemistry is an important field of study because it explains how things work. It explains cooking, cleaning, all sorts of different processes. Even though you don't know it, you are all chemists as well. You're able to make observations, propose explanations, or theories about why things happen the way they do. So as we go through our demonstrations, try to use your scientific reasoning to understand what's happening. Make a prediction or hypothesis about what you think will happen, then observe the demonstration. And finally, form a theory that explains what you observed.
So before we start, we have to go over some safety precautions. And because the demos we are doing are potentially dangerous, we need to take some safety precautions. Can anybody tell me what safety equipment you see us wearing? Wearing the hat.
Gloves, goggles,
Girl in blue.
Long sleeves.
And anybody else? The first aid kit. Okay, so yes, we all are wearing goggles to protect our eyes and gloves, and we also have long pants and shoes. Closed-toed shoes so the chemicals don't go on our feet. Okay, so when we're working with fire, there are also some precautions we need to take, and therefore that's why you see this is our fire blanket. And if there's a fire, if anybody's on fire or there's a fire that needs to be put out, we use the fire blanket, and then we have the fire extinguisher. Okay. Okay, so hopefully we don't need to use these, but if we do, it is important that we have them here in case of any emergency. Okay, the precautions are extremely important for ensuring the safety of everyone, and therefore, because you guys don't all have the safety precautions that we have, we suggest that you are far enough back from the experiments so you don't get hurt. And remember, not to try this at home.
Okay, so the first reaction that we're going to do tonight is a combustion reaction. Can anyone tell me what a combustion reaction is? Anyone?
oxidizing.
Mm-hmm. Can you give an example of a combustion reaction? Mm-hmm. Great. So when you have fuel, as you can see here, when you have fuel and oxygen and a spark, you make water and carbon dioxide and heat. The equation for this reaction is shown here, and you see fuel, oxygen, spark equals water plus carbon dioxide plus energy. So what are some examples of fuel that we use? We already heard one. Can anyone? Yes, sir.
Gasoline.
Very good. So where do you think the oxygen we need for the reaction comes from? Yes, in the air around us. Combustion reactions are really actually similar to what happens to food in our body. As your body burns food, which is the fuel, to create energy, which releases water and carbon dioxide in the process. Through this happens much more slowly than the combustion reaction we will show you here. So in this reaction, we will start with a plastic container, shown here, and we will fill it with ethanol and swirl it around a bit. It's very important to coat the whole inside of it. So the ethanol will be the fuel for this combustion reaction, and the oxygen which comes from the air around us is already in the plastic container. And now we will light a match and move away. And the match will create the spark for this reaction. As you can see, the reaction produced heat, and if you touch the container, you want to take that around and they can touch it, you will see that it is warm. What do you think will happen if we fill the plastic container now with more ethanol and throw a match inside? Anyone? If we do it again after doing it once? Yes, sir.
Fire.
Yes, but it won't cause the same exact reaction because the oxygen was used up. The oxygen that was in the container was just used up from the past reaction. So then, for a chemical reaction to occur, we need all the reactants. And if one of our reactants is missing, like oxygen, then we won't get the same reaction. So maybe it'll be less strong because it'll be less oxygen. This is like baking. If you don't have all the ingredients, you won't make the same type of cake. It might taste or look differently. And that is our combustion reaction.
So there are 3 states of matter. Can we name any of the 3 states? Yeah.
Solid, liquid, and gas.
Good. So let's start with solid. Can anyone name a solid? You in the hat?
Cheese.
Cheese. That's a good one. Very delicious. In the orange?
Ice.
Ice. Oh, that's perfect. Yeah?
A wooden block.
Good. Yellow?
A hammer.
A hammer is a good one too. So when you're in a solid, the atoms are super close together, and they can't really move because they're so close. As the matter gains more energy, though, at least with that, you can move a little more, and it turns into a liquid. Can anyone think of a liquid? Water. Yeah. In the blue. Yeah, good. Next to the boy in the hat. Milk. Yeah. In the hat. Water. And behind the boy in the hat. Great. And as it gains even more energy, the turns into gas. It vaporizes.
So gas has lots and lots of energy, and so they don't like to be, the gas atoms don't like to be next to each other, so then they expand like we did. One moment.
Okay, so now that we've talked about this, who can tell me what state of matter this is in? Gas? Yeah. Gas, but can you see bubbles in here? Yeah.
Liquid?
It is. It has properties of both a liquid and a gas. This is called nitrogen. Why is it so weird though? Is it really hot or is it really cold? In the brown? Yeah, correct. It's super cold. So, now, if water freezes at 32 degrees Fahrenheit and boils at 212 degrees Fahrenheit, how cold do you think this is? Yeah?
Negative 250?
Yeah? Let's see. Any other guesses?
Negative 2 million?
Good guess. It's actually negative 230. So you were really close.
So now we have some balloons. We're going to try and freeze these balloons. How many do you think we can fit in the cauldron?
As many as you have.
Good guess.
Anyone else? Guesses?
Yeah.
In the red?
10?
3.
3. Okay.
5.
Okay. Those are all good guesses.
But it looks like you can only fit one balloon in here. I mean, this cauldron doesn't look that big. Why? How can you fit 5 balloons in here? What do you think?
They shrink.
How do they shrink?
Well, I don't really know that. When something is cooled, it contracts.
Yeah, good. So it's kind of like our demonstration in the beginning. When things got more energy,
Spread apart.
we spread apart. Let's see what happens. I don't know if I'm doing this.
I've never seen them.
Let's keep track. That's number 1. Well, does anyone think they're just gonna stay shrunk and just like not do anything? No one thinks it's gonna happen? Okay. You guys are too smart. Okay, let's all undo. So, we will join the floor. Yeah. No more table on there. Yep. You guys see that?
So the crackling noise that's being
made is the little particles of liquid nitrogen coming off and they're being expelled into the air. So those little particles so those little pieces are on the balloons right now and they're burning off because they're so warm in the air. So that's what you hear right now. Yeah, it's really like normal. You guys want to feel them?
Okay, guys, now we're gonna create some flowers. What do you think will happen? In the hat? Yeah, in the red.
They'll harden and if you hit them with something, they'll shatter.
Hypothesis. And the turquoise?
Or maybe they'll fall on the ground like you could be crazy.
Interesting. In the red?
The petals might fall off. Yeah, I think ink will do the same as the balloons.
It'll shrink and then get bigger again. How about you and purple blanket? A lot of people think this is gonna break. Let's see what happens.
Okay, so we're gonna hit this rose with a hammer.
No.
How hard? Hit it hard. What happens?
They die.
It like shatters. Does this happen in normal roses? Yes. Yes. Yeah. It broke into little pieces. Do you guys want to break the rose petals? So the solids got really brittle and that's why they broke. Whereas the gases got really close together and that's why they shrunk. Yeah, that's good. And so we'll pass these around so you guys can feel them. Be careful not to touch the stems because as you guys are aware, I'm sure, roses have thorns and we don't want anyone to get hurt today.
Okay guys, let's focus back up here. I know the roses are super cool, but we have something even cooler than the roses. So we've done solids and we've done gases. What would happen if we did a liquid, such as bubbles? Does anyone have a guess? In the orange?
It don't blow up.
Good guess. In the front?
It'll solidify.
Solidify the liquid? Interesting. How about you?
I think there's gonna be bubbles flying everywhere.
Cool. In the hat? Okay, let's see what happens. Whoa. What do you guys see happening? So cool, isn't it? We'll take this out so you guys can touch this one too.
Why are you touching side?
So what happened to the bubbles? They're kind of hard now. Okay guys, so look at Emily. She has this pretty awesome ball. It's pretty bouncy. What do you think will happen if we put this bouncy ball in here? Yeah, with the hat?
It'll become very prone to shattering.
Good hypothesis. Yeah?
It won't become bouncy.
It won't become bouncy. Good guess. Yellow?
It'll shrink, and then if you drop it, it will shatter.
Interesting. Okay, well, we put one in there at the beginning, so let's see what happens.
I've been very
All right.
and let's see it.
It didn't count, right?
I have a question.
Yeah?
The frozen roses, since they went back to normal, are they gonna like die right away, like tomorrow, or are they just?
They'll probably die eventually, but that's more because they're out of water. I think if we put them back into water, they'd probably stay okay for a while. I mean, they've been exposed to cold. I don't actually know, but I think that they would be okay if they were still submerged in water. Because they just had a cold shock, they're not going to be exactly the same. They're probably a little bit wilty.
All right, so who can tell me what an element is? How about the superhero? Yeah, that's some good examples. How about you?
The basic thing that you like put together to make a...
Yeah, basic building blocks of matter. You guys got some ideas?
A pure substance that's not broken down any further.
Yeah, exactly. It's the building blocks of matter that chemists study. Any around us can be divided into specific elements. Yeah, you got some more ideas?
It's molecules and atoms.
Yeah, atoms are different types of elements. So you'll see some examples that will be used later on in our next experiment. You'll see something called like hydrogen peroxide that uses different types of elements. So to help us understand this better, we can think of elements as letters. And letters come together to form words, right? Just like elements come together to form compounds, just like hydrogen peroxide, which are two elements put together using chemical bonds. And compounds come together to make chemical reactions, which is just kind of like how words come together to make sentences, right? So we're going to see a lot of examples of that throughout all of our experiments today. So to help us understand all this better, we have something called a periodic table. Have you guys heard of that before? Yeah? So there's a lot of different places on here. Every element has its own special spot, and you can tell a lot by an element and how it acts just by where it's placed. For example, on this side, we have all our gases. We have things like oxygen and nitrogen, stuff like that. And on this side, we have our metals. What are some common physical properties of metals? Yeah?
They conduct electricity.
Yeah, how about you?
They make like trucks.
Make trucks, yeah. Get some ideas? Think of jewelry. What are some common properties of jewelry? Yeah?
Diamonds.
Yeah, diamonds, and diamonds are like shiny. A lot of other metals are super shiny and they're really hard too. So you can tell a lot about it just because it's placed right here. You can tell that it's going to be hard and shiny most likely. So the periodic table is really useful into getting a glimpse of what an element's going to act.
So as we saw with liquid nitrogen, adding or removing energy can change the state of matter. Does anyone have any idea of what else is the state of matter? No? Well, one example is clouds. Does anyone know how clouds form? Yes?
Condensation of water vapor.
Good. What else?
It's well, steam condenses into water.
Good. Those are really good ideas. Clouds form due to change of atmospheric pressure. Water droplets in the air get condensed, which means a lot of pressure force since the water droplets close together. Then, when the atmospheric pressure suddenly decreases, the water droplets turn into water vapor, a gas. Therefore, suddenly decreasing pressure can change a liquid to a gas. This is what happens with the liquid nitrogen. Nitrogen gas is put into a big tank under a lot of pressure, forcing it to change into a liquid. Then when we take out the liquid nitrogen out of the tank, when we take it out and put it in the cauldron, there's a lot of pressure, so the liquid nitrogen turns back into gas. Today we're going to form our own clouds. The soda bottle will be used as an atmosphere. We will add a little bit of rubbing alcohol to the bottle.
So we're going to use the soda bottle as our atmosphere. So and we're going to use this rubbing alcohol. So it's going to be like the atmosphere, and we're going to make it cloud.
It's like water droplets from the clouds. We're going to twist the bottle around just to make sure that the rubbing alcohol covers the entire atmosphere, just like real water droplets do. Now, now we will use a bicycle pump to pump air into the bottle. Do you guys think that by adding air, we're increasing or decreasing the pressure inside the bottle?
Increasing.
Increasing? Increasing? What do you think? Increasing? Increasing? Does everyone think that it's gonna increase? Yes? Yeah. So as we pump air into the bottle, it will increase because there's going to be a lot of pressure. Now, what do you think? Okay. We'll just wait to see.
Do you guys see anything happening?
So a small cloud formed. Let's see if we add more pressure.
So part of science is finding your mistakes and fixing them. And when you don't have results, you just keep trying. And that's part of the fun of it.
There we go. So, does that look like a cloud, you guys?
What do you think will happen if we pump the bottle up again? Will the bottle stay cloudy? No?
It went away, right? And now it's cloudy again. So changing pressure basically is what causes clouds in the atmosphere and what causes us to have cloudy days and not so cloudy days.
So look at all this leftover liquid nitrogen. What should I do with this? Yeah?
Dispose of it safely by putting it into the container.
Yeah.
Freeze it.
Yeah, back in the container is a great way to transport this. Yeah, what do you think?
Pour it on the ground.
Pour it on the ground?
Yeah, do that.
Is that safe?
All right, everybody, so now we are going to do a decomposition reaction. So does anybody know what decomposition is? Yeah?
Decomposition is when materials start to break down.
Yeah, that's exactly what it is. So that is what we're going to do today, right now, with this experiment. So we are going to break down a compound called hydrogen peroxide. Which is this. So the hydrogen peroxide, we're going to break it down into two parts. It's going to be oxygen gas, or steam, and water. So first, we're going to add some dish soap to the graduated cylinder. And this is going to act as the foaming agent, which means it forms bubbles. We're also going to add some food coloring. And now, we're going to add some potassium iodine. And this compound acts as a catalyst by speeding up our reaction.
This next reaction is very explosive.
So our next reaction, we're going back to our combustion reaction that we started with, like the ethanol cannon. But this time we're going to use some balloons. And each of these balloons has a different metallic compound in them. And as we saw on the periodic table, all the different elements have different properties. So each of these balloons, when we light them on fire, will be a different color. They have different physical properties. And this next experiment might be a little bit loud, so if you don't like loud noises, you can cover your ears, just as a warning. So here we have a green balloon. What color do you think it's going to explode as?
Green.
What's in it? We don't know. It's a mystery. We'll find out. What color did you guys see? Yeah. So that compound had the physical property that it turned blue. Purple. Now, what element do you think that was?
Copper.
Great guess. That was definitely copper. And that's just like the copper in the pennies that we use. You guys know what happens to pennies when they're really old? They turn green. Yeah, exactly. Nice job. Yeah, so they turn green, and that's why that exploded and it was green. What color do you think this one's gonna be?
Purple.
We'll see. What color did you guys see? Purple, yeah.
Chartreuse.
Another green one. So what is that gotta be?
Copper.
Yeah. What was the purple? The purple one was potassium.
These kinds of metals are what they use in fireworks, so that's why the fireworks have different colors. So that's pretty cool.
That looks like a snow ball. So thank you all for coming for our demonstration. Do you guys have any questions? No? Oh. The red.
The red, I think, was strontium.
What was that? Oh, you have a question? Oh, no. You can't do any of the experiments that you saw. No, you can't do it at home for safety reasons, okay?